How's it going, Phil?
Hey, did someone say something? I just realized I only have
No, I
headphones.
was just saying hello.
Hey, how's it going?
Not bad. How are you?
Good. Hey, Philip. Oh, not in yet.
Hello.
Hey.
Hey, Phil. Good to talk to you.
Hey, Simon.
Yo,
Everyone joined already. Is the early crowd? I normally give it 2 or 3 minutes. All right. So 78 people responded, which is kind of a ridiculous number. At best, I normally expect to get 30, but this is already about the number of folks that we get, and more may trickle in. So hey everyone, welcome to Hacker Nights. This is a meetup for software internals, basically hosted by my company, which is just me. If you are not familiar with DataStation, I encourage you to check it out. It's a tool for helping you query your data, whether it's Prometheus or Postgres or Influx. Anyone interested in talking about that can talk to me on Discord. Zoom chats are not recorded, so you can use Zoom chat for questions, but if you would rather it be recorded, you can join the Discord. Hopefully you can see my background, discord.multiprocess.io. There's a Hacker Nights channel. Feel free to leave questions there. I'll be checking that, or just have discussion there. Also, a reminder that this talk is recorded for YouTube. I will post the link to you for the YouTube after it's uploaded, both in that channel, Hacker Nights channel on the Multiprocess Discord, and I'll also post it to the meetup event. So that's it. First up, we've got Simon. And Simon, I'll let you introduce yourself. Take it away.
Yo, okay. I'm just gonna, can you allow me to share my screen?
Yes. You should be able to.
All right. I'm just gonna share this window here. Okay. Yeah. Hi. Yeah, this is my first time doing a talk for a long time, so it's gonna be fun. Yeah, my name is Simon. I used to be an infrastructure engineer at Shopify, working kind of the online infrastructure there. When I joined in 2013, we were doing like hundreds of requests per second, and I think by the time I left, we were doing hundreds of thousands of requests per second, which is like pretty meaningful change in infrastructure to really take you through the trenches. These days, instead of being a principal engineer within a single company to multiple teams, I work with a bunch of different companies and help them review their infrastructure, evolve their infrastructure, and things like that. Through my little company called WebScale Inc. If anyone remembers the like MongoDB memes from the early 2010s. And what I want to talk about today is like my favorite hobby horse, Napkin Math. I have a little newsletter as well where I talk about this stuff all the time. There'll be a link at the end. And in particular, I want to talk about memory bandwidth because this is by far, I think, the most versatile Napkin Math number that I use all the time when I develop expectations for both how to design systems and use them. And today, there's a lot of talks and content out there on how to get maximum memory bandwidth using SIMD, performance counters, all of the tooling. That's not this talk because that's out there in abundance. I'll link to some of the really good content on that kind of stuff. But instead of how do you take a number like 50 gigabytes per second of memory bandwidth and actually use that in practice, like in meetings and when you're designing systems and when you are querying your database. So that's the kind of stuff we'll talk more about today. But first, what's Napkin Math? My favorite example to explain it is this one from SpaceX, where essentially I'm imagining that in the early stages of SpaceX, Elon was kind of shopping around because he didn't really want to build a rocket. And so he went to presumably Russia, NASA, so on, that had their own rockets. He got probably a quote. I don't know how this works. It's probably not quite like an auto quote, but these things cost 100 million plus, right? To get one of these rockets, and then it's destroyed, right? So I'm sort of, then he looks at this rocket, right? And he's probably like, well, it probably weighs like this many tons, and probably has like roughly this much titanium, copper, and carbon fiber. Then he goes on the, London Metal Exchange website and multiplies those two numbers and said, well, like, why is the fucking elite? She gonna say me. So why you keep talking about KC3? Hey. I'm about to get the motherfucking heat. Kill this. Yeah. Why is there such a big discrepancy, right? The material cost for this rocket is in the single digit millions, but the real cost is, around 100 million. So that must be manufacturing defects, essentially how he looks at it, right? So there's this gap between the first principle mental model and the back of the envelope calculations and reality. And that gap usually presents an opportunity, right? If it's cost, well, maybe there's a cost opportunity here to make it an order of magnitude cheaper, or maybe his mental model is just wrong, right? It turned out to be the former. So an example of how this might play out in a real meeting, in a real tech company, and this is not some like shade scenario here, but something that's a variant of something that may or may not have actually happened. So you might have a product team that goes into a technical review and they're saying, we're building this product. We have to do a certain type of query to get to implement this product. And so we try to use Elasticsearch. We build a whole prototype, but it's way too slow. It's taking like hundreds of milliseconds or a second to satisfy our queries. So we can't use off-the-shelf software. We have to go build our own database to do this, right? And the review team is like, well, I'm building your own database, like, I don't really want you to do that, but like you build a prototype and you've kind of shown that I don't really have a good understanding of the system. So yeah, so sort of like, out of kind of like the burden of proof is sort of on you, and you don't really have time for that. You have your own projects to run and your own reviews, right? I'm sure many or most of you have seen something like this play out. So then the team proceeds on to this, frankly, very stimulating task of implementing your own database, but also notoriously difficult, and this project never ships, right? So then you could say, well, how does this play out if one of these like alleged individuals with some Napkin math knowledge shows up into this meeting? So same thing, product team presents this, but then instead the principal engineer is like, well, like fundamentally you are searching for 10 to 20 different terms. If you have an inverted index structure, you're, per term, you're dealing with maybe about 1,000,000 64-bit integers. You multiply that out, that's about 8 megs of document IDs in this inverted index. It's not super important to understand what an inverted index is. You can think about it like a hash map here, right? You have all these like 8 meg keys. So in order to then do a term search for about 10 to 20, well, now you have to like look at 8 megabytes a couple of times. So if it's 10 terms, it's 80 megs. If it's 20 terms, it's 160 megs. Okay, so we have that many megs. We can read that. We see that from the Napkin math. We know we can read 1 megabyte of memory in about 20 microseconds. Well, you multiply that out, and we should expect this query to take ballpark, millisecond and a half, 3 milliseconds. So, your prototype is either completely wrong, or Elasticsearch is tracking 100 to 1,000x off of the Napkin math. And then, you might be a little cocky there, and then you say, well, I know which one I put my money on. And so then the product team probably gets a little bit defensive, and they look into their prototype and they figure out that they should by the document ID, which in Elasticsearch terminology means that the document was spread across all these different nodes, and they spend all this time in Elasticsearch kind of aggregating documents and doing serialization, deserialization, when everything could be done on one node way faster, right? So now you've just saved them all of this time because they didn't have a good mental model. And probably the biggest takeaway of it all from this scenario is that like when someone comes with a prototype, do not trust them. I don't trust prototypes because it's so easy to mess it up, right? You don't trust prototypes. The only argument that I respond well to in a meeting like this is for you to present a very, very coherent, simple mental model. of how the system works and then reason up from first principle. Otherwise, I'm just not going to trust you. Good thing is that I already compiled all of these numbers for you. Is this kind of like, I've been working on these numbers over the past 3 years or so for how long does sequential memory take? How long, could you expect a bare bones TCP server to work? So you get an expectation for a database performance. How long does the random seek take, random memory? When a team comes and says, hey, I want like 200 Redises, that's unreasonable. So I got to build like this other like crazy thing instead. You say, well, that's actually not that much money. You multiply it out, it's only 20K. That's okay for us in this particular context. So these numbers, I go back to them again and again. I've worked on them over many years. They're not all completely accurate. Like right now, I spend a lot more time on memory bandwidth, so I need to update those numbers. But all of these are going to be within an order of magnitude of reality. And more than enough for you to go into a meeting like the one before. So the Napkin math process is essentially, if we deconstruct it, that you construct a mental model of the thing you have in front of you. So it could be a system like Elasticsearch, or it could be a rocket, right? You've got to get that down to the titanium, copper, or so on. It's a pretty hard thing to do. Like for me to construct a good model of something like Elasticsearch and what it's built on top of machine, like that was, some painful days in the source code and in the documentation, because this is not served to you on a silver platter. If you do that, then you multiply it out. Like the actual math, it is very easy, right? You just put that into Wolfram Alpha and you're good. And now you might be presented with this gap between expected and real performance. In Elon Musk's case, it's like, okay, well, how do we manufacture this much cheaper than NASA did? And in the case of the Elasticsearch example from before, well, it's looking into, well, why is this so slow, right? Well, okay, it turns out it ran as a distributed problem when it was much faster to do on a single node. So that's fundamentally the process that we work through. And a lot of the times also what we discover in 3 is that our mental model of the system is completely wrong. You will see on my blog, I go through this exercise on quite a few systems, and you have to go back and update the model because you can't reconcile this with the system. So memory bandwidth in particular is probably the most used number of all of them. I use this all the time. It's probably the only one that I actually have memorized. And it's useful because it's really the speed limit for how fast you can process data. Unless you're doing a lot of floating point operations, like if you're training a neural net or you're doing some kind of like, physics simulation or whatever, this is probably going to be, you're probably going to be constrained by memory bandwidth, right? Your CPU can do a lot of math, like it can multiply a lot of numbers in the time that it takes it to fetch 64 bytes off of memory. So we do this all the time. We iterate through arrays. We do all this kind of stuff. A lot of applications are limited by this in some way or another. If it's a web application, it's probably more by I/O, right? But if you're talking about like kind of a lot of databases and these kinds of systems that we design, where we spend a lot of time in the design phase, it's typically memory bandwidth that it comes down to. So what can we predict if we know this number? Well, we can predict things like how long it's going to take for an Elasticsearch query to come back. We can predict things like how long it takes to serve SQL queries and stuff like that. So I want to take you through 2 quick case studies, and then that's it. So the first one is SQL queries. So this is probably where I've applied more Napkin math than anything else. A lot of the work that I do comes back to databases, especially the good old relational ones. So if you have a query like this, where you're getting the sum of a bunch of products, it's a very arbitrary, kind of boring query, but it has enough going on that we can analyze it a little bit. So of course you could say, well, Simon, why do I need to bother to go through this 3-phase process of triggering out the mental model and do this math and stuff? I can just write explain, right? Well, the first thing is that if you haven't built the system yet, well, now are you going to go and like create a cluster, create 100 million like realistic products, put them into the database, and then at the right indexes? Like this take days, right? Like prototypes is not just inaccurate, it's also just very, very slow process, right? Someone doing that, I could sit on a whiteboard and figure this out in 30 seconds, right? It's way faster to iterate on design if you have serious facility with these numbers. It's going to be slow to start with, but you're going to get very fast at it. The second thing is that when you read that explain output for something like this, it's going to be pretty simple. But when it's a complicated query, right? Well, what are you going to compare that to, right? You don't know if that's a good plan or not. You just know if it's slow, right? When I look at a SQL query, I don't write SQL, right? I think about how do I want to traverse this data structure, and then I write the SQL, right? That's how the best DBAs I know, they write code like that too, right? They don't let the database decide for them which index to pick, right? So if you were to do a full table scan for this, there's no index. Well, then we can say, well, this table has these 100 million products. They're maybe half a kilobyte each, so that's 50 gigs. We can read them from the Napkin math numbers I showed you before, 20 milliseconds per gig, so this is about a second. If this wasn't in the buffer pool, it wasn't loaded into the cache in memory of the database, well, then on SSD, sequential reads are about 10 times slower, sometimes even faster than that. Sequential reads on SSD is really, really, really fast. So maybe 10 seconds if this was a really cold query. So not completely unreasonable if this was like in an analytics background, but if this is something that for whatever reason someone is interested in a lot, like they have a collection or whatever of their products like this, well then this is completely unacceptable. It's not just slow to the user, the database is going to cry. So then we say, okay, well, we're going to add an index, right? We add an index on this price, it's 64 bits. We multiply that out, and now our index is about a gig, easy to have in memory. We know from the bits of computer science, we know that we have to do about log 2 operations on the number of elements, that many searches to kind of figure out where 200 is on that index. Cool, we seek there. That's about these, like if this is in memory, each one of those random seeks takes about 50 nanoseconds. So this is about 2 microseconds to find that place where the index is 200. Then we scroll down, we can see that that's, about 1 million 64-bit integers. It's about 8 megs, and 8 megs takes us about 160 microseconds to scan, right? So very quickly we can develop an expectation that really this kind of query, if we have an index, should take less than a millisecond. And even if all of this is happening on SSD, we should expect single-digit millisecond performance, even if this wasn't in cache, right? So that's pretty good. So if this is taking a lot more than that, we know something is wrong, right? In Postgres, it might mean that vacuum hasn't run, so it can't do an index-only scan. Like there's all these kinds of reasons. And you might say, well, I know that Postgres does this and blah, and it has this problem. And it's like, that stuff just doesn't matter, right? We're just trying to get within the ballpark here with a pretty accurate mental model of at least how this is accessing disk and memory. And in my experience, having done this like hundreds of times, databases track the Napkin math really, 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 really well. And typically, if there's a gap, it's your model, not the databases. So I want to end off with a case study of a real application that I've been working on over the past month or two. So Causal is this really cool, like probabilistic multidimensional spreadsheet. What that means is that you can do things like you can say, I project that I'm going to make between 150K and 300K in this month. And then it can do kind of Monte Carlo simulations to give you a distribution of outcomes. That's the probabilistic part. The multidimensional part is that you can slice that. So you can say, well, I sold this many like toys in Australia by this demographic, by this user agent, blah blah blah. So you can kind of drill on this kind of OLAP structure, right? So today, this spreadsheety OLAP kind of structure can handle about 10 million cells in a few seconds, but they want to get to 1 billion. So I'm helping them kind of like figure out how to do that. It's a really good fit for this Napkin math model of thinking. And by the way, if this is something that's interesting to you, that you can come work with us on this. So in Causal, you might have something like this where you have like net revenue, cost of goods sold, and then the gross profit, right? And the profit is just the revenue minus the cost of goods sold. So if we didn't have anything multidimensional or probabilistic going on, we're going to simplify as much as possible in this Napkin model. We could assume that the array just had the number of months that we're dealing with here, right? As the elements, 100,000 is January, 200,000 is February, and so on. So then we can say, well, okay, is it like let's get a ceiling here. Is it even realistic to get to 1 billion cells? Like, do we need to create some distributed architecture for this? Someone might say that, right? If we're in that tech review, they say, oh, we can't do 1 billion cells on a single machine. We need to create this distributed architecture. So we can say, is it possible to do this on a single machine? And so we look at this and we say, well, okay, these are probably 64-bit integers. There's 1 billion of them. We multiply that together. So we have 8 gigs. They're all going to be 8 gigs. We multiply that together. We have 24 gigs. We go to the Napkin math reference, blah, blah, blah. Half a second. Okay, that's reasonable, right? We can probably head within 10x of that. So between 500 milliseconds to 5 seconds, right? So this is actually not a crazy thing to do on a single system. And then if we divide that into 10 million, then the example we showed before, it could take about 5 milliseconds. But today, 10 million takes about 30 seconds in Causal, right? So why is there this, 4,000x discrepancy between the Napkin math and Causal, right? So this is, again, we have this like first principle gap, right? There's this huge span between what the expected lower bound of the performance is and what we observe in real life, right? And again, it's like we have this gap. So either our understanding, our mental model of the system is out of whack, or there's an enormous opportunity here. So in this case, it's the latter. There's an enormous opportunity for performance. So if we look at the data structure and don't look at this in detail, right, we can see that there's kind of this map, and you index the map to get to the individual cells. So this is, the sales in Australia for this product at a particular point in time. You do that, and then there's a pointer to the node. The node here is the cell, and then the cell holds all this information about like where are we in time, what variable do I belong to, what dimension am I? Like am I in Australia or am I in Canada? Then we have things like the formula, right? This might be a dynamic thing. Then we have like the values, and it could be a distribution of that. So we have all this stuff, right? And this whole struct is 88 bytes, right? It's huge. So if you multiply that out, right, 1 billion times 88 bytes, I can't tell you offhand what that is, but that's a lot of memory for anything to deal with and traverse over just on its own. So if you look at this, right, and you spend a bit of time on computer architecture, you're like, well, maps are slow, pointers are slow, and the node is huge. Okay, so if we could improve these things, we would probably speed up this system, maybe even get that 4,000x performance increase that we have sort of established as our lower bound, right? Because when we're executing this code, that the CPU it's literally crying, right? The only way that the CPU knows how to cry is to increment the performance counters in the CPU. But if no one's looking at them, it doesn't know, right? So we have to look at those. We have to have a bit of mechanical empathy with the machine we're dealing with, disassemble profiles to try to figure out what's going on. So I'm kind of skipping ahead here, right? Like this, it's not like this, I just look at this and then I know. I just like some painful weeks. But we can sort of look at this and say, okay, like this map, how bad is this map? Well, we have to hash it. It takes a little bit of time. Then we have to do a random read to get into the map. And then we have to follow this pointer, which is somewhere else in the heap. So we're doing this like zigzagging, right? Whereas if we're doing sequential memory access, it's just like that, right? And the CPU can't predict that we're zigzagging around in memory like this, finding pointers, right? So the CPU is trying to like, oh, maybe he's going to load this, maybe he's going to load this, but it's wrong all the time. So this presents a huge opportunity cost. The CPU doesn't know what memory to preload, right? And that's the bottleneck here. If this was in sequential memory and we're just kind of doing what we did in the initial example of going through these arrays and multiplying values, well, the CPU knows like what lines we're going, can predict it really easily. So this is 25 times faster easily. So I tried to implement this, right? And I'm seeing just like with some native easy Go code, that this is about 19 times faster, just writing this out quickly, right? Literally just changing from an array, from a map to an array for this, right? So it's not quite 25 times, but it's like close enough that we don't completely destroy our mental model here. So the random reads are probably slightly faster, and maybe the prediction is a little bit better than we anticipated here. And there's all kind of caching going on that's hard to reason about, but this is pretty good, right? And then the node is huge, right? So the actual size of the cell is huge. It's all of this data about the formula and stuff like that. Maybe we can move that into some parallel data structures that are indexed at the same time. So we've removed we banned pointers and everything is an index now. So we know our index, and we can then index into another data structure to get the formula if we need it, or where in time we are, right? But most of the time when multiplying integers, that's just a lot of garbage that we're getting in and out of the CPU caches that we don't need to deal with. So we kind of see, as we decrease the size of that cell and analyze it, that things get a lot faster. So we can then see that if we then went to just literally an array of floats, which is kind of probably a bit unrealistic, then we're about 36 times faster. That's not quite the 4,000 times, right, that we had on the Napkin math. That's at 5 milliseconds. So why is it still like 350 milliseconds? Well, the first thing is that when I'm generating all these nodes, I'm using some RNG generators to get a random floating point number, and that's actually quite a few operations. When we're on the scale of this, that might be counterintuitive, but if I remove the RNG to generate these random numbers that I'm multiplying, then this goes down to like 10 milliseconds. So we're spending all of that time. Memory, so multi-threading will help because it just gives us more core to generate random numbers on. Then there's SIMD. So my Napkin math takes into consideration that you're using SIMD. It probably should call that out. And Go doesn't SIMD by default. Like I had to disassemble it to figure that out. It doesn't do that, doesn't auto-vectorize. And then we could even go beyond that. We could start to compress this data, compresses really well, and then use all these cycles that we have between getting memory to decompress. So compressed data can actually be much faster to read from than raw memory. We could use a GPU, which has really, really high memory bandwidth and could be really good if we're doing a lot of like heavy floating point operations and that kind of thing. So that's pretty much it. I will end with this quote here that that I really believe that first principle thinking is required to break out of this iterative improvement cycle and to make these kinds of order of magnitude improvements that we're talking about here. If you're interested in this kind of content, I have a newsletter where I, every few months I publish an article on this kind of stuff, and there's some on my blog. And here's a couple resources. You can go to syrupsm.com/memory-bandwidth to get to this slide deck. I don't think it's going to be public from the website, so just remember that if you want to look at some of these different URLs. That's it. Thank you very much.
Awesome, Simon. And sorry about that. That has not happened before. I locked the meeting for a second and enabled the waiting room. New folks should be able to join now in the waiting room. But yeah, I want to open up the floor to any questions for Simon.
So with Napkin math and this methodology, in a real world scenario that's not completely data driven, so something that's like an organic business to business type application that grew over time from brick and mortar to someone who just the type of company that just does like a digital transformation. The type of scenario I've seen most often is where they're trying to determine at what point should a particular service or set of services be sharded. Like, how do we calculate when is it time to go from one SQL cluster to two SQL clusters, two SQL nodes to one node to a cluster, and so on. It doesn't seem like Napkin math would be the right tool for that, but I would love to be wrong.
Oh yeah, you can totally use Napkin math for that. I've done it a couple times. So I should write an article on this. I don't really have an easy answer to this because it's not like you can just look at your Datadog graphs and then be like you're good or you're not good. The way that I've done this exercise before, right, is like there's kind of two paths, right? Are you what's your growth on reads and what's your growth on writes? There's a fundamental ceiling for how many writes that you're going to be able to do in like a non-sharded environment, right? When we made the decision to shard Shopify back in like 2013, right? It was because, well, fundamentally, we need to support this many thousand checkouts per minute. And fundamentally, that is not possible on a single writer. Then you plot the growth and you say, okay, well, we're going to hit that in a year. So we better get started. So writes, writes is the easiest one to do. Then on the read front, right? Well, yeah, again, similarly, you can look at what kinds of reads you're doing, and how taxing they are. Typically, you're going to have 5, 10, 20 or so queries that are going to be 80% of your load. In my experience, you look at those, you look at the growth of those, whether they're fundamentally very poor on a SQL cluster or not, and then you go with read replicas first, right? But with that kind of thing, I'm always worried about the writes first. There's so many workarounds to getting read replicas working well. Yeah, but I mean, if you want to talk more about this, like maybe you can DM me or something like that, because if this is a decision you're in front of right now.
It's not. It's just not. It's one I've encountered several times, and it's always hard to convince stakeholders without going through extensive meetings and discussions where you try to show them, yes, we are in fact bottlenecked. It'd be nice to be able to point at some numbers that look authoritative and point to a resource that is authoritative and say, look, this says we are bottlenecked. for sure.
Yeah.
So
I think it's some good encouragement for me to write a blog post on that, because it's a very common question and it's very, very influential, right? And if you make it wrong, you're gonna really spin your wheels.
appreciate it. Thank you.
In the interest of time, I'm going to cut off questions for Simon. But if anyone else has other questions, I think Simon does hang around in the Discord. And if not, I'll ask him to send me some, or maybe let's keep it in the Discord, especially after we've got random people coming on here. The Discord might be a safer place. Phil, it's all you.
Cheers. I'll also need to share my screen. So let me see how this works. All right, give me 1 second here. This is not okay. Let me try. Okay, 1 second. I will just rejoin in 1 second. All right, I am back. I had to restart the app to be able to share my screen. So let me see if I can share it. Oh, all right, let me see if I can share. Oh, here we go. Great. Right, are you seeing my screen, Phil? Thumbs up? Okay, great. All right, let's present. I am on my wife's laptop, which I'm not used to. So it's always a challenge. So let me see if I can keep this going. Okay, great. My name is Philip O'Toole, and I am going to talk about rqlite tonight. Thanks for Phil to reaching out to me, and many thanks for Simon for that interesting conversation. Phil, how much time do I have so I just make sure I don't run over?
I don't. Officially, it ends at 9, but if it has to go over, that's totally fine.
That's fine. This is a shortened version of a presentation that I have given before. The long full version is something I gave to CMU a couple of months ago, which is available from my website, which is linked from the slides. So I will try and pace it. Some of this stuff is deeper, deserves a deeper explanation, but I'm going to jump over it in the interest of getting through it, but it is a shorter version, so I think it's timed. But I'm going to talk a little bit about tonight about the rqlite, which is a distributed database built on the Raft consensus protocol, and SQLite. Hopefully everybody will get something out of it. I touch a little bit on coding. I'll try and fit a demo in. We'll talk a little bit about distributed systems. And the goal here for people who are interested in this is to show how I took an off-the-shelf distributed consensus library and an off-the-shelf relational database and stuck the two together. And in fact, if people are out there interested in building their own distributed databases or distributed system, there's a lot of really easy to use libraries that you can put together. Go happens to be the language I program in, but if you're a Go programmer, you can build a lot of interesting programs yourself today, and hopefully this will give people an idea of how to do so. A little bit about me very quickly. I'm an engineering manager at Google Pittsburgh. I was previously a full-time developer on the core team at InfluxDB for a few years, and I have led various other software teams. Phil mentioned Influx, I think, at the start. It's an open source time series database written in Go, which definitely influenced a bunch of my thinking in this project. And Simon mentioned Elasticsearch quite a bit, and definitely at least the API here, who was also influenced by my experience with Elasticsearch, which I've used. This is not related to my work. This is something I just do for fun outside of my work at Google. So what is rqlite? It's a distributed relational database which uses SQLite as its database engine. It's open source. It's written in Go, though it imports plain old vanilla C code for SQLite. So the goal of this presentation is to at least give people a high-level understanding, if they don't know it already, what distributed relational database which uses SQLite actually means, and places to jump off. For those who aren't Go programmers, Go can call into C code. There's a fair amount of performance overhead, but it can do so. And that's how I wrote rqlite in Go, but I'm able to make great use of the SQLite source code. And rqlite is currently at version 7.3.2. So what does it look like? Let's from the user point of view, this is where, if any of you have used Elasticsearch, you'll kind of notice a simple HTTP API where you can write to the system by posting some data, and you via HTTP endpoint, and you can read it back. And what you send to it is standard SQLite commands in a structured HTTP request format, and it'll insert the records, and then you can read them back very easily through the HTTP API as well. And this is a demonstration of what the session looked like. Of course, we're going to show how you do this on a distributed version of SQLite. But generally, it's quite easy to interact with this thing with rqlite, which was one of my goals. So the first thing people ask me is, why do this? Why would you take SQLite and try and build a distributed database out of it? There's two reasons. First reason is SQLite is a really solid database, all contained in a single C source file. It's rock solid. It's probably the most widely deployed database in the world. But of course, it runs on a single machine. So it's rock solid. I could just pull down a world-class database and plug it in. Why replicate it? Well, with replication, you get reliability. If I lose all my data on one machine, well, it's still on another machine. Maybe it's a machine in the same rack. Maybe it's a machine in a different data center. Maybe it's a machine on another continent. So with replication, you get some fault tolerance with your data. I really enjoy writing code in Go. And with Go kind of statically links everything by default. So rqlite is just basically a single binary that you can just drop on your machine that you built it for, and it just runs. It's a really simple deployment. And it's pretty lightweight to operate, very, very easy to operate. So you don't have to spin up a heavier distributed database like Postgres or MySQL. Now, the only thing is rqlite may be too simple for your needs, but what it does well. And the other thing is, why is it a distributed system? Simon kind of actually touched a little bit on this. Distributed systems are actually kind of a pain to operate sometimes. So why do we have them at all? The reason we have them is distributed systems give us reliability, right? Data is located in multiple places and computation is available in multiple places. So that's the first reason that we run distributed systems. The second reason we run distributed systems is they sometimes will provide scalability. Not always, but they often are more powerful. And people often confuse these two or conflate these two reasons. There are two reasons to run distributed systems: for performance and reliability. Often systems do both at the same time. Elasticsearch is an example. rqlite only does one. It does it for reliability. There's a certain amount of performance improvement on the read side, but rqlite is a distributed system for fault tolerance and high availability, not for performance. So I spoke a little bit about SQLite. It's a world-class relational database all inside a source file. And what I did was I took that, combined it with a consensus protocol, which I also didn't write. And the consensus protocol is Raft. So what is Raft? So Raft is a distributed consensus protocol. What is that? So a distributed consensus protocol is a well-defined algorithm that promises you that a set of machines will all agree, or at least a quorum, but I'm just going to be rough about it. A set of machines will always agree what the given value of a variable is. And you might say, well, that doesn't sound that exciting. But actually, to do that properly, when machines could go down, when they could fail over, when they're out of sync with each other, when messages between them get dropped, is actually surprisingly difficult. And so what Raft does is it is a protocol based on what is called a log of changes, where every machine will agree what the state is of a given variable. In practice, it allows us to build clustered systems, right? You can say, I'm going to have 5 nodes, they're all running Raft, and every node in that cluster will agree what the state is of a variable, in theory, with the detail with respect to the leader. But if there's a canonical answer to the there's a canonical answer to the question, what is the state of X? Raft doesn't make any statements about what that state is or how it's manipulated. It'll just always promise that the changes are made to every node in the same sequence. Now, what I did was I interpret the state as an entire SQLite database. So now I have a system where every node agrees on what the state of a SQLite database. Each node has a SQLite database underneath. And that means if I lose one node, I can always go to another node. If I lose that node, I can go to another node. As long, of course, as there's a majority of nodes up and running. But that's basically what a distributed consensus protocol is. Graphically, it looks like this. So now we'll get into a little bit into design. I'm rushing through this, Phil, so I'm happy to take questions at the end, but I know there's a lot here.
You don't need to rush too much. Again, it's fine if it goes over.
Okay, so let's spend a little bit of time. So this is a graphical representation of what I just mentioned. The 3 nodes represent 3 nodes running the Raft consensus module. Now, people may be interested, where did I get this Raft consensus module? It's exactly the same consensus module that is running inside HashiCorp Console or HashiCorp Nomad, if anybody is familiar with those distributed systems. The HashiCorp team very nicely wrote their open source Raft module in a way that is easy to apply its distributed consensus logic to any other state machine. And that is the key for folks out there that would like to try and build their own little distributed system. In Go, you can start with it. But what is Raft? In this example, there's a 3-node cluster. You have a special node called the leader and 2 other nodes called the follower. And what a client can do is a client can send a change to the leader, and the leader will replicate that change, or the cluster will actually replicate that change to every state machine, which in this case is a SQLite database under the Raft nodes. And so what you actually do in practice is send SQLite statements to the leader, and the leader will replicate that SQLite statement to every follower, and every follower will then, and leader, will apply that statement to the SQLite database. So there's a real abstraction here. The Raft system just says, you gave me a stream of bytes, I will make sure that that stream of bytes is sent in the same sequence to every other node. And the Raft consensus system will even do that if the leader dies and another leader is elected and so forth. It's only at the low-level SQL layer that the bytes are unpacked and said, apply this to the database. And so now this way, you've got a SQLite database under each node that's exactly the same. Applying it to the database is called committing. So that's it. Now, if we jump into one of these nodes, let's take a look at the architecture inside it to give people an idea of what a single node looks like from an architecture point of view. You've got a HTTP API, which receives requests. In practice, if you go back here, I show a client talking to the leader, but actually you can talk to any node because every node exposes a HTTP API. And if you are not speaking to the leader, rqlite transparently sends your request to the leader. But every node is running a HTTP API. Every node is running a Raft subsystem, and every node is running a SQLite database. And I'll go into a little bit of detail here because if people can understand the little bit I'm going to say here, you'll learn a lot about distributed systems. In this example, when a write comes into a rqlite node, it goes through the Raft log first. And the Raft subsystem makes sure that every other node in the system agrees that that write has been received in a specific order. And once the Raft subsystem agrees in that write, then each node applies it to the SQLite database. The key thing to notice here is reads do not go through the Raft log, the Raft subsystem. Why is that? Because reads don't change the state machine. So it is only changes that need to go through a distributed consensus system. Reads can just go to any node and read their local copy of the database and get back the results. And that's what this diagram is trying to show. In the more detailed presentations, as I've linked, I break this down a little bit more. But this is a key thing in distributed systems. The changes are always the slow part, because they are the part that needs to be sent out to every node, make sure they're applied, often before you return to the client. But reads, depending on your consistency requests, can just go straight to the local copy and return. You get into little details like what if one node isn't caught up with the leader and so forth. But this is how this is a model that many distributed systems use today. There's a bunch of other things that go on here. There's backup and restore and statistics and so forth, and how nodes talk to each other. But this is the green part and blue part of this diagram blown up here. So now, let's talk a little bit about cluster practicalities. Because of the nature of Raft, most clusters are practical when you have 3, 5, 7, or 9 nodes. Notice you pick odd numbers. Some people will know this, but let me explain why you don't run 4-node clusters or 6-node clusters. The reason you don't is even node clusters don't get you anything extra versus I can't remember if it's the lower node beneath. And I'll show you why. In the Raft subsystem, I've been saying that every node will agree on a state. What actually happens is for a cluster of a given size, and this is common across a lot of distributed systems. It's the same in the Elasticsearch masters. It's the same in Zookeeper. The minimum number of nodes that must agree when you make a change to a distributed system like rqlite is the number of nodes divided by 2 plus 1. So for 3-node clusters, 2 nodes must agree, which means you can tolerate a failure of 1 node. For a 4-node cluster, 3 nodes must agree, which means you can tolerate the cluster of a failure of 1 node. So a 3-node cluster and a 4-node cluster have exactly the same fault tolerance, 1 node. It's only when you get to 5 that you can tolerate 2 nodes, and so on for 7 and 9. And that is why distributed systems of this nature always run odd number of nodes, because running an even number of nodes doesn't get you anything. So that's the first important thing about rqlite. The other thing is, after about 9 nodes, the system isn't really that practical. You can run it, but 11, 13, you're starting to really get to diminishing returns with regards to how many nodes you can run. The other question I actually get asked a lot about this is, can rqlite, does the Raft consensus protocol, is it suitable for thousands of nodes, right? On cell phones, I've had people say, can I run rqlite across all the cell phones in AT&T's network? And I go, no, that's not going to work, because those nodes come and go all the time. There's never going to be enough around to form a quorum. This is about running a tight distributed system, maybe that's at the center of your infrastructure. That's very important. So for programmers out there, particularly Go programmers, let me show you all you have to do to hook in your favorite state machine, which in my case was a SQLite database, into a really cool production distributed consensus module. When you are integrating with HashiCorp's Raft open source code, again, the open source distributed consensus model at the core of Causal and Nomad, you just have to implement 5 functions. Apply, which is take the series of bytes that the Raft consensus system has agreed on is next in the series, and apply it to the database. In my case, that's a SQLite statement. Snapshot, which returns a snapshot of the state machine, and restore and persist, which write those state machines to disk. And then release, which isn't that interesting, so I won't talk too much about it. But like I said, apply is what applies to the state machine. Snapshot, restore, and persist is to support a feature called log truncation, because Raft works by appending commands to an ever-growing log. And if you think about it, what's stopping that log growing without bounds? So snapshot is a way that you take a snapshot of the state machine and then truncate the log. Some other systems do that as well. So yeah, so for Go programmers out there who'd like to play around with building their own distributed consensus system in Go, the HashiCorp Raft open source code is a great example. And up in GitHub on my own personal profile, I have a reference implementation of how to take a simple map and make a distributed key value store out of it using the HashiCorp Raft system. So folks might be interested in that. I'm happy to ask questions along the way. I'm not paying attention to stop. If people have questions, I'm happy to stop, or I can take questions at the end. But just to let you know, I'm happy
I had
for this to be
a
interactive.
I had
Sure.
a question on the previous slide. I was wondering if adding a node to a cluster to be an even number, does that actually increase your liability, like make it less desirable than having fewer nodes because there's more points of failure?
It doesn't. It just doesn't get you anything, right? So if you have a 3-node cluster, it actually makes it a little bit more liable. It's a complicated subject and I'm not an expert. So if you think about it, if you go from 3 to 4, you're no more fault tolerant. If one node goes down, you can only tolerate 1 node failure. In a 3-node cluster or a 4-node cluster, if you lose 2 nodes, your cluster is basically stopped until you can add more nodes onto it. Doesn't mean you've lost your data, but you can't make any more changes. So it doesn't get you any more fault tolerance, but is it more susceptible for failure now that you have more nodes? Maybe. The other thing that can happen is, does adding that other node, make processing, if one node fails, you're okay. Is the second node slower than all the other nodes? I haven't really done much thinking in this area, but it doesn't give you anything and it just consumes more resources, right? You have to run another node, it's more to monitor. Does it increase the chances that you'll have more node failures? I don't actually know in practice, but I know for a fact that it doesn't bring you any benefits. Sometimes people might add another node because they're going to retire another one, right? You want to add a node before you pull one out. That is often what people do, but really you don't run even nodes in practice. I don't know if that answers your question, but I haven't actually studied the problem super closely.
It answers it enough. Thank you.
Okay.
Phil, I had a quick question to one of your earlier slides. You mentioned that in the Raft log, are you putting the entire SQLite database in every entry in the Raft log?
No, good question. No, just every individual statement, right? So create table.
Oh, so you're using the write ahead log or something?
No, I use well, not the right. No. So what happens is, say a statement comes in called create table. The create table statement comes in the HTTP API. First thing it is, and that's only about whatever, like 40 bytes. It gets written to the Raft log. And then asynchronously, there is a thread, a Go routine that is constantly checking that log. And when it sees a new entry appear, it then calls, whatever it is, the SQLite API to say, write this statement. Does that answer your question, Simon?
Yeah. No, I thought I heard something about like the whole like database being in the logs, and I was like,
No. That's
I thought I heard it wrong, but I was wondering because there's like quite a few ways to
no, that'd be terrible.
Makes total sense.
Yeah, but I did mention that you have to snap. It's a good question. However, if you remember what I just said there, if you looked at the Raft log, it would be every single write that was ever written to the database would be in a separate entry in that log. That could grow forever. So what you do is Raft has a technique whereby it snapshots the SQLite database, writes a copy of that to disk, and then truncates, in other words, deletes from the Raft log every entry that is in the log that is now in the database. So that's what snapshotting is about. And then the state of your system is remaining Raft log entries plus a copy of the database. Does that make sense? That's where you might have heard me say, occasionally you have to take a snapshot of the database. And I liked your performance talk because I've written quite a bit of study of the performance of this system, and it's definitely IO bound because the one thing you have to do here is, in practice, the SQLite database is in memory, but the Raft log is on disk, and there has to be an fsync every time an entry goes into the Raft log to say I'm persisted. So the insert rate is really bound by your disk performance. It's only when you're getting to running rqlite nodes in DCs that are more than about 90 milliseconds apart does the network latency really start to overwhelm the disk latency. The more detailed presentation I have at the link from the end may be of interest to you. But yes, it's only individual entries. So if I go back to the very start and show the API, this insert statement, that's what is in the Raft log, right? And then if there was another insert statement, that would be in the Raft log, and so on and so on. So where was I? Let's do a demo. Let me see if I can make this work. Let me see if I can. So let me see stop share. Right, so I will share my desktop here. I think that will work. You're seeing the desktop? Okay, great. So folks should see 3 shells here. So hopefully this is not too small. What I'm going to do is I'm going to launch 3 rqlite nodes by hand. Now, the good news is I have a lot of support for Kubernetes, but I'm just going to show you this. We're going to launch 1. Let me see this. Launch 1. And this comes up. And I'm going to launch another one, which tells it to join the first one. Do that. And I'm going to launch a third one. And now we have a rqlite cluster. So one thing I like is it's really fast to, people can see the JSON output there. Okay, great. So this is all 3 nodes. This is the first one. This is the second one. And this is the third one. I'm running through this quickly. I have this demo all on the rqlite webpage. And if we look, this first node is the leader. Let me see if I can find that. Let me see. Here we go. So it is the leader, whereas the other 2 are followers in that little diagram that I wrote, that I drew back here. It's this is a follower, and this one is a follower. Now let's connect to the leader node. Though I could actually connect to any node but let's connect to it.
Why does it matter that there's a leader?
Well, that's how the Raft consensus protocol works. All writes must go through the leader, right? That's how it works.
You mentioned though that I thought you mentioned that it didn't matter which one you sent it to.
Yes, I'm talking kind of quickly. I have built the HTTP API in rqlite that if it receives an insert request and it is not the leader, it transparently forwards the request to the leader, waits for the leader to return, and then forwards the request to the client. So I'm talking about 2 things.
Gotcha.
In behind the scenes, only the leader node can make the write, but rqlite on the layer it has on top the HTTP API that takes care of it all transparently for you. A lot of systems work like this, but like Elasticsearch works like this. If you write to an index that isn't on the local node, Elasticsearch transparently sends your request to the other node that has the shard, writes the request, and comes back. Now, Elasticsearch is a very different system, but most systems kind of work like that. They try and hide it. So now we have created a table. Select and wrote in records to it. I connected to the, let's connect to the other node, a follower node. Let's see the same thing. The records are there too. So very quickly we spin up a cluster. For fun, let's kill the leader. Now, let me show you that it's gone. If I refresh the leader, no response. Let's take some other node is going to have become, this is a demo, so you never know. This is, okay, node 2 is still a leader. So let's see if the other one became the leader. Actually refresh. Let's see. Yes, it became the leader. So that was node 3. So now we can't connect to the first one. It's dead. Connect to the second one. It's there. And we can connect to the fourth one. And let's select star from foo. The records are still there. I could insert more records now. I could restart the other node and we'd pick them up like the all. So that's rqlite, and that's how it works. And I have a lot of other functionality, but I will get back to this. So let me stop the share and share the presentation again one last time. So very quick. I know we're running out of time, so I don't want to take too much time. So that was the demo. It's all documented. For the programmers and other people, let me tell you about the lessons. I've been developing this system for over 8 years. Some lessons learned about developing an open source database for 8 years. First one is, there's a famous programmer, he's dead now, called Fred Brooks, and he wrote a famous book called The Mythical Man-Month. And what he said was, plan to throw one away because you always will. And I found that to be true. Early versions of rqlite suffered many problems because you don't really understand a software problem until you've solved it at least once. So early versions had a poor API. They didn't use the Go database layer very well. Didn't have great Go code. I used another opt consensus module at the start that was written by a friend of mine who actually used to work at Shopify. I don't know if you never came across Ben Johnson, Simon, but he is an old colleague of mine. He wrote a node consensus module, which I used first, that I subsequently swapped out for HashiCorp. And the early versions of rqlite didn't support systems like Kubernetes that well, but the new versions play very nicely with Kubernetes. But it's interesting, if you build a piece of software that people find useful, they'll even use terrible versions of it. So that was interesting to see. But yes, I threw away many versions until I finally got it in good shape. So some of the lessons learned. What is in the future of rqlite? I would like to build distributed transactions, which is actually a pretty complicated topic. I have a design principle with rqlite is unless I'm absolute or very sure that what I am about to add remains coherent with the code that is there, I don't add it. So even after 8 years, I do not have distributed transactions. I have a different type of transaction, but it's not distributed. I would love to have more client libraries for it. It's a very simple HTTP API. I have Go libraries, JavaScript, and Python, but I would love better Java libraries, C++ libraries. So if anybody is interested in contributing to an open source project, I'd love better client libraries. And it'd be nice to build a graphical user interface, right? So I didn't have to query it all the time through the command line interface. But it's lots left to do there. So what can rqlite do? With it, you've got a lightweight and reliable distributed database built on one of the world's best databases. I think the niche use case for rqlite is part of a larger system where you need to store some critical relational database without having to run something heavier like Postgres or MySQL. And you know, a lot of people run their database infrastructure in the cloud today. It's what I do at Google. But sometimes it is nice to have complete control over your database infrastructure and know exactly where your data is and who can access it. And rqlite is, I think, it's one of the easiest distributed databases to run. So that is it. Like I said, I went through a lot of things rather quickly. I have a bunch of links there in the slide to longer versions of this presentation and some other resources. So thank you very much. Happy to answer any questions.
Aren't you selling yourself short, comparing yourself to Postgres? Like, because it's not distributed. Like,
it's not, you're right, but there are distributed versions, or if you running a heavier version of it in the cloud or something, yes and no. I think people have still think Postgres is or fully fledged database, but there are distributed systems out there, and I have lost a lot of years in my life trying to run Elasticsearch. It's a great system, and other systems, not to ding on Elasticsearch, but Simon put it in my head. And one of the things I've tried to do with rqlite is make it the easiest distributed database to run in the world, but it's not a toy, right? It's a real system. So there's a startup in Israel that is using it. One thing I've noticed, and I say this last thing, I kind of find it funny. I seem to have a lot of interest in the Bitcoin mining community for this database. I'm not sure why, but I think it's because those type of people like to run their own software from top to bottom, from bottom to top. And they find this an easy database to run for their whatever they're doing and storing in a distributed system. So I'm free, so I'm happy to answer any more questions. I'm not rushing. I just wanted to make sure I finished on time.
I had a question. It was just kind of related to what we were talking about before. So presumably your throughput is like hundreds or thousands, like a fraction of what SQLite can actually do, right?
You're absolutely right. Yeah.
And I was just thinking, I did some analysis of MySQL like a year or two ago, and I was kind of thinking, okay, well, is the number of fsyncs that a database could do like equal to the number of writes that a database could do? And my assumption was like, yes, those two numbers must be the exact same. But what I found is that SQL or MySQL sort of like pauses for a few milliseconds to see if it can group commit a couple writes at a time.
Right.
Is that an optimization you considered?
So some people so what's interesting, as you can guess, is I have a batch interface where if you send 100 SQL requests in one Raft request, as you can imagine, Simon, the performance goes through the roof, but you have the same problem. You have to wait, the client has to wait around and gather them up. It would change the semantics of the system, because what happens right now is the HTTP API, when it returns to you, that data has been committed to the Raft log on a quorum of nodes. So You could, but it'd be basically like doing a bulk, right? You'd have to wait around until you got a bunch of them to write to the system. It's a very similar idea. It doesn't support it right now. And your intuitions are spot on. With a 3-node cluster running in, say, each node in a different Amazon zone, on SSDs, I get about 150 inserts a second. So you're spot on. And you're right, if SQLite can do like tens of thousands a second, right? So yes, but about, I have to give you credit, Simon knows his napkin map because his order of magnitude is spot on. About a couple of hundred a second is about what you can do. So that's what I said. This is not about, you can store very large data sets in here, but this is about storing the critical pieces of data that you want to model relationally. It's as fast as Causal, right? Or etcd, which is slightly different because they have the same limitations. So the way I like to think of rqlite at the start was, it's like Causal, but with relational modeling available. Whereas Causal from HashiCorp is just a simple, well, it's not simple, but it's a key value store. So think of Causal, but with relational modeling available. So you could, Simon, and there's a bulk API, but then the client has to wait around. But yes, you get enormous upgrades then in performance. But then you might lose your data, right? If somebody thinks they've written it, but it's actually sitting in a batch somewhere, not actually committed, then you're.
Yeah, it's just if you're looking for something front to right, I think the way that MySQL does it, right, is that it sort of like waits around for like a millisecond or something like that, right, and then blocks all the. Yeah, it's anyway. Maybe someone's open source contribution.
Yeah. So I did try one optimization, which people might be interested in. I said, okay, I'm maxing out the disks. What can I do to reduce the number of bytes written to disk? And I said, I can compress the data. So I compressed the statements I get before I write them to the Raft log, and it didn't make any difference at the disk. Why not? Because fsync works at an atomic size of 4,000 kilobytes. So unless the original statement was larger than 4,000 kilobytes, compressing it from 200 to 20 didn't make any difference, because the OS, as requested by Raft, is going to fsync after every entry, and it's going to fsync an entire 4K or whatever the block size is. So it didn't help, but it did help with network transfers, right? Because it was the data that was being transferred between nodes was compressed, but it didn't actually speed up, didn't increase the insert speed. But
so it would introduce some more than slight instability into the system. But have you considered using memory mapped I/O in SQLite to perform your read and write operations in order to speed it up? Since you're working in a cluster anyway, you can handle a failure of a single node.
Yeah, you could. So a couple of things, just so we're clear. The SQLite database is actually completely in RAM. So you can run it on disk if you want, but the SQLite database is completely in RAM. So the writes to the SQLite database don't generate any I/O. It's perfectly safe because it is the Raft log on startup that rebuilds the whole SQLite database again. Now, to your point, I think what you're saying is, imagine you ran every node in memory only. Then, yes, you get the performance, amazing performance, but you're vulnerable if you lost the entire cluster. But it is interesting. The startup in Israel that I mentioned they do exactly that. They have they didn't tell me exactly why they do this, but they have their canonical data stored somewhere else in a non-relational form. And what they liked about rqlite is its ability, it was fault tolerant, but not persistent. And they did exactly what you said. They ran the 3 nodes completely in memory, including the Raft log. That did mean that if they lost the cluster, they lost all the data, because everything was stored in memory. They couldn't restart the cluster from a persistent state, but they just reloaded the cluster from from another source and started up again. So they got very high insert rates, and they got fault tolerance, but they didn't have persistence. I hope that makes sense, because they just would say, okay, the cluster failed, let's just reload the whole thing from etcd or something. But then they were able to query the data in a relational fashion from whatever else they were doing.
So like several others, I'm sitting here puzzling about how to increase performance there. And I joined late, so apologies if my question just kind of misses the mark or doesn't make any sense here. But I'm curious if, so it sounds like your IO bottlenecked on the Raft, on writing through the Raft leader.
Correct, yeah.
Have you
Well,
have you
yes,
considered?
every node writes to its own local disk, but yes, it's the Raft log, correct?
Okay, so maybe not the Raft leader. I was going to ask if you had thought about sharding the requests coming in so that there are multiple leaders in the cluster.
Yep, yeah. So that is something that people think about. They say, could you somehow have multiple Raft nodes going on at once or across multiple systems? The answer is yes, you could, and people have implemented this. They call it multi-Raft. If you punch that into my employer search engine, you'll learn about it. But it's a whole new level of complexity, right? But yes, you could. People do that. They call it multi-Raft to try and improve the performance. Or the other thing people think about this is to try and improve the performance by sharding the SQLite database across different nodes. And there's lots of different dimensions you can do. But if I did that, rqlite would no longer be the world's easiest to operate distributed system. I can tell you that, right? Suddenly, you know what will happen. So yes, you are. But with that kind of performance, suddenly the system is going to become way more complicated to run. But yes, people type in multi-Raft if you're interested in learning a little bit more about that.
Yeah, cool. Thanks.
Maybe I missed it in the beginning, but you made it sound like Raft was, well, Raft is just one choice. Did you explore others in the beginning, and have you explored other options since? Like what's made you stick with it?
The reason I went with Raft is the very library I use, unless they've changed it since I left a few years ago, was the consensus module that was at the center of InfluxDB. So I got a lot of familiarity with this and went to that. I did consider making one change. etcd, so there's two major Raft implementations in Go, and Raft is available in a lot of different languages. If you go to the Raft homepage, you'll find this. So for folks out there, the concepts are the same, it's just different languages. There are two major Raft implementations written in Go. One is inside Console, written by HashiCorp, and the other is inside etcd, written by the etcd. And etcd claim their performance is better. I don't know how they do it and whether they really mean it. And I suspect, Simon, they are actually doing the batching that you spoke about. And that if I look into the details, I'll find there's different guarantees about the right performance. I have considered swapping their one in for HashiCorp to see if it would make a difference. But I'm one person working on this project, and ultimately I have to think of all the other things I could do and what would get me more users of this database, swapping in a different consensus module that might be 10% faster, or writing a better Python client library. Probably writing a better Python client library, right? Or a better Java client library. But yes, I have thought about it, but I've decided that my time is better spent elsewhere. Cool.
All right. Since we're a little bit late here, I'll turn it off and turn off the recording and leave the Zoom on. If anyone wants to hang around, you're welcome to.
Yeah, I'm happy to stay on for another 15 minutes if anybody has any questions. Otherwise, yeah.
And yeah, I'll be posting this on YouTube. Links will be in Discord and on the event, on the meetup event. If anyone attending here has any ideas for who to invite next, I am always looking for suggestions. Or if anyone here is interested yourself, you don't have to be a professional. These guys were awesome today. That's I gave a presentation and it was nowhere near the bar. So whoever else should not feel too stressed out about presenting if there's something you want to talk about. Yeah, thank you, everyone. I'm going to turn off the recording now, and the floor is everyone else, yours.